With this lecture, we're going to continue our inexorable march towards kind of an introduction to just about every different kind of chemistry. At least that'll be true by the end of Chem 106. What we're going to be talking about now is obviously electrochemistry. And believe it or not, we've actually seen electrochemistry before. We just haven't really talked about it explicitly. So first of all, just a definition. Keep in mind that there are certain reactions where electrons actually go from one atom to another, right? And so there's an example on this next slide of one such reaction. You notice it's a really simple one. And what these processes all depend on are these things called oxidation and reduction reactions. And usually if you're a cool kid, you just call it redox or something like that. And it turns out there's actually those two things always go together, much like an acid always needs a base. An oxidation agent also needs a reducing agent. And we'll talk about all those terms eventually. But what we can see here is that we've got good old zinc, right, that started off with a zero charge. And we know this thing is overall a zero charge is because that's always assumed anytime it's not written, right? And so no matter what was here, right, if it was like 10,000 different elements, the fact that there's no little charge written, it turns out that that thing has to overall be neutral. And of course, this thing, it's pretty easy. If this overall thing is neutral, it's only made of one thing, so it's got to be a charge of zero. We see here this proton, right? And that proton has a +1 charge. And what is actually happening here to change this charge from its original 0 to a +2, and then, of course, hydrogen over on this side has an oxidation state of 0, is that electrons have actually been transferred from the zinc to the hydrogens, right? And so one of the things that really confuses people in this topic is this idea that when things become positive, they've actually lost something. So that's something that we're going to have to kind of contend with and wrap our brains around a little bit. But it's important to recognize that anytime you lose electrons, that is considered an oxidation. And you might wonder, why the heck did we call it an oxidation? Well, back in the early days, we actually thought that everything that was oxidized literally had an oxygen kind of get stuck onto it. It just turns out that it's a little more general than that. Oxygen is obviously, like O2, for instance, is a really good oxidizing agent, right? It's really good at stealing electrons. So they used to think that it had to do with your number of oxygens, but now we understand it actually are these little tiny electrons that are going from one place to another. So here, since zinc loses 2 electrons, we would say that that thing is being oxidized. And then you consider the other part, and just like the two-handed clap of an acid with a base, you always need the other side, right? If something's being oxidized, there must also be something else that's being reduced. And of course, the 2 electrons that are given up by zinc are absorbed by hydrogen. And because of their gaining an electron, and again, this is really confusing, it actually goes a unit of charge less, right? It actually becomes kind of 1 unit more negative. And in this particular case, since it just went to 0, it's just, gaining 1 electron apiece. So we got to talk a lot about these like really confusing terms. I absolutely hate for at least introducing this subject. It's actually super interesting, but so many of the words are really, really confusing, right? So it turns out, so we just talked about the fact that zinc was oxidized, right? So zinc went from a zero a zero oxidation state to a +2 oxidation state. Well, it turns out that thing that did the oxidizing of zinc was actually hydrogen, right? And so it's crazy to say this, but whatever is reduced is the oxidizing agent, right? So I always have to repeat this to myself to kind of wrap my brain around these terms. And I say an oxidizing agent is itself reduced. And then, of course, the opposite is also true. A reducing agent is itself oxidized, right? And so we would say that zinc is oxidized and it is a reducing agent, right? Because it actually is kind of forcing its electrons onto hydrogen. And of course, one of the interesting things before we get into oxidation numbers here is that if you figure out a way to have this like process that just kind of happens spontaneously happen maybe in one compartment over here and then another compartment over here, and you run some, some sort of wires from one side to the other, you can actually get work done, right? And that's the basis of a cell, or probably more commonly termed a battery, right? You're actually taking those electrons that just naturally want to escape from one thing to another, and you're powering different devices, right? So you could imagine, at least in theory, right, we could put like our cell phone right here, right? And our cell phone, if it's fully charged, actually has a site of oxidation kind of going towards a site of reduction. Usually in the case of those things, they're these pretty fancy lithium ion batteries. But, it's pretty much the same idea, right? In those batteries, lithium is losing an electron and something else is gaining them. Everything about redox chemistry involves understanding oxidation numbers. And of course, it's pretty easy to figure out the oxidation numbers in this last example, right? But the problem is that oxidation numbers can get a little bit more complex. So this very first day, we're just going to spend a little bit of time talking about how to determine oxidation numbers. So what is an oxidation number? Well, it represents the number of electrons lost, gained, or unequally shared by an atom, right? What it does not necessarily indicate is its actual real life charge. It sometimes does, right? So what do I mean by that? Well, if you go back here, right, zinc's actual charge is 0. Zinc 2 plus's actual charge is 2 plus, right? Or you would say its oxidation state is also +2, right? Those two match. Well, it turns out that you can have situations where you're talking about something in a covalent bond, right? And we know for a long time, we've known that covalent bonds don't involve the complete loss or gain of electrons, but you can have an unequal sharing, right? And so oxidation numbers really sometimes can confuse students, because it seems like we're kind of going back on what we said about covalent compounds, but it is actually not the true charge of something, right? It is, it's kind of, I almost think about it like a bookkeeping method that sometimes matches reality and sometimes doesn't, and it allows us some predictive capacity, right? And so I think it'd be helpful just to kind of take a glance at a couple of different oxidation numbers and then just see at least one or two examples of kind of how to figure out these things. So here we've got some different nitrogen species, right? Well, if you look at these charges, it's kind of confusing because they don't actually match, right, the charges that we would typically write on like an ionic charge list, right? Usually nitrogen, if it's an ionic compound, is a 3-. Well, it turns out that is one possible oxidation state. It's not on this list, but that is one possible oxidation state of a nitrogen. But nitrogen has a ton of oxidation states, and keep in mind, these are not actual charges, right? These are just kind of representing if these things were ionic, right, what its charge would be. But we know these things are all covalent compounds because they're, they have covalent bonds. Anyway, so how do you figure out oxidation states? Well, it's actually pretty easy if you just remember that by convention that nothing is written up in the upper right here, that the overall charge is 0, right? So each one of these things, the overall charge is 0, right? Well, I guess this guy, right, his overall charge is a -1 over here because there's a minus written. So how do you figure it out? Well, it's pretty easy if you're just made up of two different things and or I should say the same two things and your charge is 0. Well, obviously both of those things are going to be 0. What happens in this kind of thing, right? Well, how do we end up with that +1? Well, it turns out what we're going to do is we're going to learn about what I might have called in Chem 104, I called them the goalposts of the periodic table, right? Kind of the closer to the edges of the periodic table you are, and definitely the higher you are on the goalpost of the periodic table, the more likely that you're going to have an oxidation state that kind of matches your charge. So oxygen itself, that's pretty long-winded, sorry. Oxygen itself, right, that is kind of closer to the edges of the periodic table. So we're going to use oxygen and its normal charge of 2- to figure out, well, if this thing is overall neutral and oxygen has a 2-, how many oxidation states, or how many positive charges must each nitrogen have? Well, it turns out +1, right? You've got 2 times +1 is neutral when combined with that 2 minus. Right? And so we would say that the nitrogen there has an oxidation state of +1. Similarly, same kind of thing. If this thing is overall neutral and oxygen has a 2 minus oxidation number, nitrogen must be +2, et cetera, et cetera. And so we could kind of play this same game. And of course, finally, we get down to this last one that adds up to a -1 overall. Well, then you just have to make sure that you've got 3 2 minuses for a 6 minus, right? And what does nitrogen have to be to end up with an overall charge on this thing of a -1, right? And you'd say, well, its oxidation state must be +5. So the good thing is that most ions, right? Or I should say most, kind of the metals that are involved in normal kind of ionic compounds, they actually have oxidation numbers that kind of match their expected charges, right? So here's just kind of a list of some different possible oxidation states. You get down here though, like once you get to things like iron that are in the transition metal region, it turns out that all irons don't have a 3+ charge, right? There can be irons with a 2+ charge, and those actually correspond to real life charges, right? But so what you don't need to worry too much about, like technically you're supposed to use like a 2+ for an oxidation state, and then like a 2+ for an actual charge and a +2 for an oxidation number. I don't play that stupid game. I can never remember. So, for us, like +3 and 3+ is going to mean the exact same thing. Let's take a slightly more complex example here and try to figure out the oxidation state for sulfur here. Just to make sure that we're clear about it, right? We've got this guy, which is an overall charge of 0. We're going to use the goalposts to kind of figure out that oxygen is a -2. There's 4 of them. And then hydrogen has a +1 charge almost always. It can have others, but since this is an acid, we know that this thing donates H pluses, therefore its charge must be +1. Oops, and it looks like my presentation is a little funky monkey here, but what you can see here is that we've got 2 plus charges from a hydrogen. We've got 4 -2 charges for the oxygen. And so the idea is just kind of simple algebra, right? How do we make this thing overall neutral? Well, we need to make sure that sulfur overall has a +6 charge, right? That's the way that we get this thing to be completely neutral. For something like this thing called oxalate, if we're going to determine, let's say, the charge of carbon, we're going to do a pretty similar thing. We'll use oxygen's -2 charge, figure out that it's an overall -8. What does each carbon have to have in order to make this thing a 2- charge? Well, it means that we have to have 2 carbons with a +3 charge, right? So you would say the oxidation number for, oops, that should say carbon right there, sorry. +3 is the oxidation number of carbon because there are 2 of them present, and so the math works out such that we get a 2-. So I'm going to end with this particular thing here, and this is just a helpful way of remembering what in terms of electrons, what is being oxidized and what's being reduced. And that is oil rig, and oxidation is loss and reduction is gain. And of course, you can just memorize it, but I find it a heck of a lot more helpful to do that. Another helpful way to think about oxidation and reduction is to kind of think of it as a number line, right? And so anytime you're moving kind of towards the positive side here, that's always going to be an oxidation. And remember, that is the loss of electrons. And then anytime you move on towards the more negative side here, that's going to be a reduction or a gain of electrons. So hopefully this presentation kind of gives you an idea of what we're going to be looking at in the pretty near future here. And if you have any questions, please feel free to ask.